Hi again, Chris Tisdell here, everyone. Thanks for tuning in. In this presentation, I'm going to continue my series of videos on calculus. And in particular, we're going to answer the question, if I take a curve and I rotate it about the x-axis, I form a solid. How can I compute the volume of that solid? Well, we're going to use calculus, and in particular, we're going to use integration. So I'll step you through an example and I'll give you an idea of where the formula comes from. So let me share my screen with you. Okay, here is the example we're going to work with. We have got a curve, 2 minus sine x, and then 3 straight lines. And we're going to rotate the region bounded by that curve, or think of these as sort of edges to the region. And we're going to rotate that about the x-axis. We'll form a solid, and we're asked to compute the volume of that solid. So first of all, there's a lot of curves going on here. There's a lot of information. So let me draw you a picture, and we can do it. For that, I'm going to use GeoGebra. Okay, you can see the red curve here is the curve 2 minus sine x. The vertical purple curve is the line x equals 0. The blue vertical curve is the line x equals 2 pi, and the green horizontal curve is the line y equals 0. So basically the green line is the x-axis, the purple line is the y-axis, the blue line's x equals 2 pi, and the red line, or the red curve, is the curve 2 minus sine x. Now, what I'm going to do, if you just watch my mouse for a second, is I'm going to rotate this about the green line, the x-axis, right? So to do that, just imagine I've sort of reflected, if you like, the curve, and then I join them using a sort of a circular rotation to get some sort of vase or something, some sort of vase solid. Okay, so that's a little bit of an idea of geometrically what's going on here, but how do we solve it? Well, let me share my screen again with you and we can get down to business. Okay, essentially what we can do here is apply the following formula. Now I'm going to let V be the volume of the solid, and in this case we're interested in this curve and this line and this line. Okay, that gives us an idea of where to how to frame our formula. Okay, now where does this come from? Well, I'll talk about that in a minute. For this particular example, our f of x is 2 minus sine x. Our a would be 0. Our b would be 2 pi. And this is the formula for the resulting volume of the solid. Okay, so I'll tell you where that comes from in a minute. So let's put those values in. I can take the pi out the front because it's a constant. And I get 2 minus sine x all squared. Okay, so what I can do is expand this bracket. And I'm going to get 4 minus 4 sine x plus sine squared x. All right, so now all we need to do is really knock over this integral. There's a couple of ways of doing it. Firstly, sine x between 0 and 2 pi, it basically the areas cancel out. So you know that the integral of sine of x is going to be 0 from 0 to 2 pi. With sine squared x, well, we might move to a double angle formula there. So let me just write that out. Now we know that sine squared x is equal to the following. Okay, I've just squeezed that in. Okay, so if we do these integrations separately, what we see is we're going to get 4x there. We're going to get positive for cosine x. Now, really, the integration there is not necessary because you know the integral of that's going to give you 0. You're going to get a half x there, and here you're going to get negative 1/4 sine 2x. All right, so when you plug these numbers in, that's going to give you 0, that's going to give you 0. This will give you 8 pi, this will give you pi. Oh. And so we get 9 pi squared. Okay, so this is the volume, and it would be in cubic units of the solid when you rotate the region bounded by these curves about the x-axis. Okay, now the question is, where does this formula come from? Well, that's an excellent question. Glad you asked. Let me give you a little sketch of where it comes from. Okay, so this is not a derivation, but just a little sketch. You've got, say, a curve, and if you're working between, say, A and B. What you do is you rotate that curve, or the solid. Yeah. Oh, sorry. Let me let me share my screen with you. Okay, so you've got some sort of curve given by a function. You've got A and B there. And what does this formula remind you of? Well, pi times something squared, maybe pi r squared. This looks like the formula for the area of a circle. And indeed, if you look at the cross sections of this solid, so you slice it, so you get circular cross sections, the area of this, well, how can we compute that? It's just the radius squared times pi. Now the radius here is f of x, or just y, so pi r squared. And what you do is you can compute little disks by slicing this whole thing up and computing the disk, and then adding up all the volumes of the little disks. That's where you get your integral sign from. So the way I look at this, it is just the cross-sectional areas or shapes are circles, and you just use the formula for the area of a circle and sum up to get your integral formula. So that's a really brief snapshot of where this formula comes from. Okay. Anyway, I hope you enjoyed this presentation. Remember to always try to draw a picture when you're working on these problems. I sort of cheated a bit and used GeoGebra for that one because I thought it would be neater. But drawing a picture gives you a good visualization and visual understanding of what's going on. If you have any comments, any questions, always love to hear them. You can put them in the comments section. Thanks for watching. See you later. Bye.